Okay, so welcome back to another video. So here we have an infinite sum we'll be dealing with. We have 2 to the power 2 to the power n plus 2 times n, so that exponent's all by itself. All this being divided by 1 plus 2 to the power 2 to the power n, that quantity, and then square. So we're actually going to be taking a little bit of a different approach rather than your standard, brute force / manipulation. So what we'll be doing is that we're actually going to make the claim such that the following, instead of the infinite series, it's the finite series. It is actually equal to some closed form. And to prove this claim, that we're actually going to be using some mathematical induction. So if we can actually prove that using that strategy, then all we have to do is once afterwards, we could just actually take that limit as it approaches infinity, and then we get our desired result. So nothing needs to be said, nothing. This is just one of those other strategies yet to, go around with. I'm sure there's several other ways to do it, but we're actually going to take this into, the fun approach, at least the way I see it. So with that, let's actually just jump right in. So our claim that will actually be is that the following finite series, so now we have that the upper index is going to be m, so n is equal 0 of 2 to the power 2 to the power n plus 2n, then divided by, so just the given series just like that. So we're actually going to say that this is actually going to equal to the following closed expression of 2 subtract 2 to the power 2, then to the power n plus 1, then plus 2 to the 2 times n plus 1, all this being divided by, so that means 2 to the power 2 to the power n plus 1, and then subtract 1, then quantity square. Okay, so with this now, let's actually go on and actually start the proof. So as we know, when it comes to mathematical induction, you start off with your base case. Here is our base that we started with n is equal to 0, or m is equal to 0. Then another way is that we can also do for m is equal to 1, 2. Once you get through that, you have to show that the k is equal to m is assumed to be true. Then afterwards, using that assumption, you're going to have to show that the next step, aka k plus 1, is true, and then so forth afterwards. It follows from there. So with that, let's actually just start off with the proof for m is equal 0. So we plug m is equal 0 over here, so that means the infinite sum, or rather the finite sum, is that it starts at 0 and ends at 0. So n is equal 0, so that means 2 to the power 2 to the power n, then plus 2 to n. So it's just the same thing again, so 1 plus 2 squared, then n, and then square. So if I just put in the lines in between, so I just put everything for 0, then you'll notice that this is actually just going to equal to 2 divided by 9. So let's actually make things a little bit different and rearrange it so we actually get something of this similar formulation on this right-hand side. So let me put it equals over here, so that means this 2 over 9 is the same thing written as 2, then subtract 16 divided by 9. And then if we utilize that algebraically a little bit differently, that's the same thing written as 2 subtract 2 to the power 4, and then divided by, so that means on the bottom is 9, but I can write this, so we have a minus 1 over here in that expression, so I can write this as instead 4 minus 1, and then square. Okay, so with this in mind, so let's actually now notice that if you play around a whole lot, you'll get that the following, so 2, and then subtract, so 2 to the power 2 to the power 0 plus 1, then plus 2 times 0 plus 1, all this being divided by, so 2 to the power 2 to the power 0 plus 1, and then subtract 1, quantity square. This shows that this is the same thing equal to the same thing over here as you plug in 0 from there. So that actually validates that. So continuing forward, let's actually go into the m is equal 1 case. Let's actually just do a little bit of that double check. So that means I have the finite sum, the upper index is 1, n is equal 0 of that same thing of the given. And then we expand this out, so that means I have 2 divided by 9, so that's just evaluating at n is equal 0, so when you evaluate that for n is equal to 1, so that means that gives us 16 divided by 25. Okay, so let's actually rewrite this a little bit differently. That's the same thing written, that we know that we just wrote 2 over 9 is the same thing written as 2 minus 16 divided by 9. So 2 minus 16 divided by 9, and then plus 16 divided by 25. So interestingly, we can actually rearrange this a little bit differently. So that means I have a minus, and then minus until that actually comes down to just 2. Then minus 256 if you just do the math. So minus 16 divided by 9 plus 16 over 25 is minus 256, then divided by 225. In other words, that's the same thing written as 2 minus 16 squared, and then divided by, so that means that's actually going to be what, 9 times 5, so that means that's going to be 15 square on the bottom. In other words, it's 15 square. Then let me actually erase this so we can actually write this a little bit different. We know that's 16 square and then divided by 15 square. So in other words, you can write this a little bit differently to say that this is the same thing as 2 to the power 8. But remember, we're just trying to get this in a similar formulation just like here. So that's why we have to do a lot of this rearrangement. And on the bottom, that means I have 15. So in other words, that's the same thing as 16 minus 1, then quantity square. And in other words, if you actually play around even more with that manipulation, we have that this is 2, and then subtract 2 to the power 2 to the power 1 plus 1, and then plus 2 times 1 plus 1, then all this being divided by, so that means I have 2 to the power 2 to the power 1 plus 1, and then all this being subtract 1 quantity square. That's the same thing as over here, and then that actually validates all that, so that means therefore that the m is equal 1 case is true and the m is equal 0 is true. So our base case really is actually fulfilled, so now let's actually get into the assumption that m is equal to k is assumed true, so let's get to that. So to write this out, to expand this out, so k, then n is equal 0 of the same thing, the following 2 to the power 2 to the power n plus 2 times n, then divided by 1 plus 2, then to the power 2 to the power n, and then divided by, it's supposed to be a 2 over here. Then we say that this is just simply just equal to 2 minus 2 to the power 2 to the power k plus 1, and then subtract 2 times k plus 1, all this being divided by, so 2 to the power 2 to the power k plus 1, and then subtract 1 quantity square. Okay, so we assume that's true. So now what we have to do now is, let me actually switch to a different marker for this. So now next we have to show now the next step, the predecessor, so m is equal k plus 1 is true as well. So moving forward, that means now, in other words, if I expand this out, so that means now there's going to be k plus 1, then n is equal 0 of 2 to the power n plus 2n, then 1 plus 2 to the power 2 to the power n, and then quantity square. So we expand this out, really, that's in other words the same thing written, so we have that, we just add the k term, we assume that's true, and then we go to the next step, so the k plus 1. So now, really what we have is the infinite sum, or the finite sum, k, then n is equal 0 of 2 to the power 2 to the power n plus, so essentially it's just the same thing written as just over here, except our upper index is going to start from k in this case. And then lastly, just put this for the k plus 1 term over here, so that means now we have 2, then k plus 1, then plus 2 times k plus 1, all this being divided by 1 plus 2 to the power 2 to the power k plus 1, and then quantity square. Okay, so with this in mind, let me actually erase this side and then we can actually just continue forward. Alright, so to continue forward, so I still have a little bit of space left, so I'm going to continue forward from there. So to continue the expansion, we assume that the m is equal k case is true, so we can actually do that substitution, replace that with 2, then subtract 2 to the power 2 to the power k plus 1, then subtract 2 times k plus 1, all this being divided by, so 2 to the power 2 to the power k plus 1, then subtract 1, then quantity square. Then we just add this with this term over here, so now 2 to the power 2 to the power k plus 1 plus 2 times k plus 1, all this divided by, so 1 plus 2 to the power 2 to the power k plus 1, and then quantity square. Okay, so as we see from this step over here, that we can actually factor out some terms. Specifically, we can factor out the 2 to the power 2 to the power k plus 1. Well, I'm just gonna say that whole exponent over here. So continuing forward, so I have 2, then minus 2 to the power 2 to the power k plus 1, and then add this with 2 times k plus 1. So beside that is the parentheses over here, that what we can do is now let's actually just get that common denominator for these two over here, so yielding us, so now the bigger parentheses are already written, so we have 2 to the power 2 to the power k plus 1, then add this with 1 quantity square, subtract, so 2 to the power 2 to the power k plus 1, and then subtract 1 quantity square. Basically, this is just going to be with addition, so that's why it was just reverse. Those terms were reverse. So now we have the same thing over here, so that means 2 to the power 2 to the power k plus 1, then subtract 1. Let me write add 1, that's what I wrote in my notes, times square, and then 2 to the power 2 to the power k plus 1, and then subtract 1 quantity square. Okay, so that closes that off. So this is just skipping the tedious step, but you'll notice that the next step we're going to do is we're actually going to expand these terms out, and we're going to have that once you expand the 2 to the power 2 to the power k plus 1 for, these quantity squares and do the subtraction, that's going to cancel out. Same thing for over here for the plus 1 and then the minus 1, that's going to cancel, but the only thing we're left with now is, so equals 2 minus 2 to the power 2 to the k plus 1, so plus 2, then k plus 1. Okay, so here's what we have. So in the numerator, we have a quantity of 4 multiplied by 2 to the power 2 to the power k plus 1, and then divide by. So if you expand this out, really what you're looking at is this quantity times this quantity and all that square, and you'll notice that you can actually apply the difference of squares to actually get something even more reduced. So we have 2 to the power 2 to the power k plus 1, then square, and then left with minus 1, and then that closes that off with a quantity square after that. Then continuing forward, so yes, there's even more coming up. So we have 2 minus 2 to the power 2, then k plus 1 plus 2 times k plus 1 in that quantity. Then to continue expanding this out, I have 4, so that's the same thing written as 2 squares. So everything over here is just actually do a little bit of like the reduction. And you could actually do the same thing over here, so that means 2 to the power 2 to the k plus 1, then square that. If you reduce all this out, doing all that simplification with algebra, we're gonna get, so 2 to the power 2 to the power k plus 1, then add this with 2, all this being divided by 2 to the power 2 times 2 to the power k plus 1, then subtract 1, then quantity square. Then we can actually reduce this even further by actually just doing the distributed property for this term back into here. Then simply just equals to 2 minus, so now we're gonna have a fraction over here. So 2 to the power 2 to the power k plus 1, then add this with 2 times k plus 1 plus 2, and then plus 2 to the power k plus 1. All this being divided by, so 2 to the power 2 to the power k plus 2, then subtract 1, and then quantity square. And then continuing on, so this is actually going to be the last step, so thank goodness for all that tedious work. We're going to simply come down to just 2 minus 2 to the power, so that means I'll just actually 2 to the power 2, then I'm going to put this in parentheses, so k plus 1, then plus 1, so that was where the substitution would be originally. So again, this is actually in terms of just simplifying things out. And then simply now lastly, I have plus, then 2, then multiply with, so k plus 1 and then plus 1. We want to end this form just so we have that the k plus 1 term is true, that actually we just do that substitution to put in that closed form over here. You'll notice that you just put k plus 1, we're actually going to get exactly just what we're looking for over here. And then afterwards, all this being divided by, so simply reduce to just 2 to the power 2, and then put this in parentheses, then to the power k plus 1, and then add this with 1, then subtract 1, and then quantity square. So we get exactly what we want to actually plug into the same formulation. So that actually closes that off. That's a check. So that means it's actually by mathematical induction, this actually holds for all the natural numbers. So now continuing, well, n is equal to 0, 2. Then continuing forward, so now the last thing we have to do is now just take that limit as m approaches infinity. So meaning, therefore, if I just say that this is the limit as m approaches infinity of our given sums, or rather that finite sum of the claim we just proved, so n is equal to 0, and then 2 to the power 2 to the power n plus 2n, and then all this being divided by 1 plus 2 to the power 2 to the power n, and then quantity square. So if we actually just go to now continuing forward one more time, so the limit m approaches infinity of our claim that we just did, so 2, then minus 2 to the power 2 to the power m plus 1, then add this with 2 times m plus 1, all this being divided by, so 2, then to the power 2 to the power m plus 1, then subtract 1, and then quantity square, close that off. Then simply we'll notice that as this approaches infinity, you'll notice that the denominator is actually getting way more larger than it is the numerator. So that means this is actually just going to approach 0. And so therefore we're actually done. So that means therefore the final answer is that this is just going to approach simply just the number 2. And just like that, that finishes our evaluation that we wanted to calculate this infinite sum. And there we have it. Hope you learned, in order to do strategy instead of having to take things the other way around. So yeah, It's pretty cool if you ask me.